Morning.
How's everyone doing? The light's better.
Yeah.
Too early.
When it gets too early and if the lights are off, I will be unreasonably
So lights on. Yeah, 9 a.m. I think I'm going to mention this all second half of the semester. I'm not a morning person, but I am becoming one by teaching this class. So I also have like 2 hours in my day where I can go for a run, like before my baby wakes up, and then right after she goes to sleep before I get sleepy. So I'm actually thinking, because I'm getting up for this class, I might start switching my friends to the morning. So it's a weird time in my life, I guess. I've tried this before and it didn't work, but we'll see. Isn't Maxine the cutest little baby you've ever seen?
When there was a ton of snow, did she get to experience the snow?
Yes. You want to see a picture?
Have you done a snow angel? I love when they put babies in the snow and then they move their arms.
We don't have one of those, but I do have.
Snow beer.
Okay, I'm just showing you all of the pictures. Okay, next class I'll bring the snow pictures. Oh, here we go. So we just went for a little snow walk. She's small enough, we just put her in like one of those little plastic Tupperware tubs and attached some strings and just pulled her through the snow. It was amazing.
What a dream.
I know, right?
To be like a little baby just in a plastic box.
Yeah.
Completely warm, getting pulled through the snow.
Totally. What a dream for her. Also, what a dream for me to pull the cutest baby in a Tupperware through the snow. How are y'all doing? Sleepy? Do y'all like feel the end of the semester coming?
Yes.
Okay.
Nothing.
You go. Oh my goodness. Yeah. My first year in grad school, I just remember like the end of it. It was a 2-year program, a 2-year master's program, and at the end of the first year, it was like I could just barely wait for the summer. I ended up taking a summer course, but yeah, spring semester was just like I was just so ready to be finished. And then I kept going, so that's weird. Yeah, great. So graduating is nice. You should definitely go to graduation. That's my hot take. Yeah, you get to wear like a fancy uniform and look cool. Go celebrate afterwards in your gear. Okay, you all want to do some work? Okay, that's more enthusiasm than I generally expect at 9 a.m. So we have somewhat of a big one today. We have like one small thing we didn't get to with simulation last time, but we're going to start extending our numerical methods approach. We're going to look at a first kind of example of using numerical methods to estimate models. So that's where we're going. I think we're gonna get through all of this today. I'm hoping in general we can do one notebook per class. We'll see how things go. That's how I have it organized on the website. So that's where we're going. You want to talk about the checkpoint real quick? This is an experiment for me. Y'all are my guinea pigs. I think quizzes are a little boring and a little uninspiring and unfun. So what I'm trying to do, my job as an instructor is to give you all the resources to succeed however you feel comfortable. To give you all the resources no matter like what level of success you're looking for. I'm hoping to make that possible for you. One of the things I want to encourage is we're doing methods in this class. And I mean, most things are learned through practice, but methods especially are learned through practice. So what I'm trying to give you is an extra chance to do the practice. So in some ways this is, like in past semesters, this class has had quizzes and group homework. What this is aimed at doing is trying to kind of pull those things together and give you an extra chance. Like I'm gonna be right there with you. I might not be like in the exact same room, but I'll be right next to you. So this gives you sort of extra chance to, have conversations about the actual work you're doing. I think sometimes like we can turn the class into class time into like a practice session or like where I give you extra work to do in class, but we have a lot of material to get through too, so there's a bit of a trade-off. So what the checkpoint is intended to do, and this is the experimental part, is to give you a chance to sit down sort of with me to walk through some of these problems, and if you have questions as they arise, we can chat about them. If you want to do this on your own, like at home, you just send me an email and I'll send it to you. But you have to do the work. Like the default is that you're going to be in the room with me doing the work. This is not like me checking in on you. I know sometimes people go out of their way to design classes to make it harder to use AI, and that's just entirely not my purpose. You can use AI like as much as you like. The intent is to get you working in sort of a collaborative space. You can, I anticipate most of you will be there kind of around the same time. So this can also give you a chance to work with your classmates on the checkpoints. So that's my thinking about it. If it feels like it's onerous or burdensome, you let me know and we'll do something different. But you didn't sign up to be my guinea pigs, but here we are. So sound okay? So next week, you'll on Thursday, you'll tell me if you liked it the week before, and then we can sort of stay flexible. But I think this will be more fun. That's really the big point. All right, sound fun? We don't know. All right, so let me just, do y'all like a recap at the beginning? I think sometimes it's a little boring, but maybe just getting ourselves off the ground for a second. So simulation, essentially what we're doing is, if we have an idea of what the underlying data generating process really is, we can just use Monte Carlo simulation to collect a bunch of fake data and then perform statistics on the fake data. And the fake data coming from the underlying distribution, using the law of large numbers, will give us an estimate of the true underlying sample statistic, whatever that is. So what we did is we actually, I'm going to run some of these things because we'll end up using it later. We talked about the law of large numbers. The law of large numbers is like a weaker version. It's like the baby version of the central limit theorem. The central limit theorem gives us both the middle point, but also the shape of the distribution of the samples. The law of large numbers just gives us that the middle point of the data gets close to the truth. So the big idea was this picture. It was like if we took 10,000 observations and we just like randomly sampled from a two-dimensional uniform distribution, and then took a bunch of samples and then checked whether they were inside or outside the circle, which we can do mathematically, right? We take two numbers, we can just use the Euclidean distance and check whether the values are inside or outside the circle. And then we can just figure out the ratio of the observations inside versus outside. I'm sorry, the total number and the samples that are inside. And this, if we take a large enough sample, should give us an approximation of pi. So this is, I think, a really nice visual way of communicating what Monte Carlo is doing. We talked about the convergence. So as we take larger samples, according to the law of large numbers, our estimate will get closer and closer to the true value of pi. So here I have different sample sizes, and then these are estimates of pi. And you can see, comparing this to the analytical solution we did right before this. When we have some extra information about the structure of pi, using an approximation of pi and then extending the number of polynomial terms, that was actually a better. It converged more quickly than just a pure Monte Carlo. The power of a Monte Carlo is not that it converges quickly; it's that it's very flexible. We don't have to know anything really about the structure of pi to be able to do this. All we need to know is that it's going to be the ratio of points inside versus total points. Okay, so this is nice. You can see though, it converges very slowly. So even after, 100,000 observations, we still don't have 3 digits of pi. So this is really nice. It's flexible, but it doesn't converge necessarily that quickly. It turns out with modern computers, it doesn't really matter. All right, we skipped this exercise, but if you're interested, you can use some of this information to approximate E. So the second thing we did, and I'm sort of getting a sense that that some of the underlying theory here may be a little shaky for some of you. We have these econometric techniques using that are sort of built on this foundational idea of the central limit theorem, and then using the general linear model or regression to fit a line. We essentially have, you can think of a scatter plot, and then we just try to draw a line through it where we're tuning 2 parameters, the intercept and the slope. When we have just one, let me just draw a little picture really quickly, just to give us a bit of a primer here. I had some good questions about this, so I just wanted to talk it through. So let's say we have, our y variable. We're just in a univariate context. We just have one variable. We're just thinking about where the center point of the data is. We can just, collect a bunch of observations. Let's say, so we have the horizontal axis here doesn't mean anything. It's just to sort of separate the data. Our univariate general linear model or regression model just gives us the average. So if we're picking a line through this data, we just have one parameter. The equation for our line looks like this. So just y is equal to some intercept parameter, beta 0, plus epsilon. We're just trying to pick where, it's just a horizontal line, and we're just picking where the intercept parameter lives. Every time we collect a new sample, that sample will look slightly different. And this generates what we call sampling error. Every time we draw the sample, it looks a little different. When we go to fit the intercept, that intercept will be at a different place on the vertical axis. If we were to do this like 10,000 times, we would get a distribution of model parameters beta 0 that looks like this. According to the central limit theorem, the distribution of model parameters is going to look normal, and it's going to be centered on the population slope. So imagine a histogram, this is just the distribution of beta zeros. And this is simply due to the distribution of sample means, right? So we're just picking the sample mean using the model parameter, and we get this distribution. This same idea applies not just with sample means, but also with sample slopes. So we can do exactly the same thing with slopes. So if you have two dimensions, so we have an x variable, so now it's a predictor variable, and an outcome variable. We collect a bunch of data. Now we're not just picking the vertical intercept, but we're picking the slope parameter as well. So this looks like something like this. So this is y is equal to our vertical intercept plus beta 1 times x with some error. And here, not only do we have a slope, an intercept parameter that gets us close to the truth. In this case, when we have a slope parameter, the intercept parameter is not the sample mean, it's just the mean intercept term. But according to the central limit theorem, we also have a distribution of sample slopes that are centered on the true sample slope. So we'll call this, let's say, mu1. So this is just the true underlying slope in the data generating process, what we call the population slope. So this is all for the central limit theorem. This is where it comes from and why it's so incredibly powerful, is because we don't actually have to see the underlying population slope. We don't have to know anything about the underlying data generating process to be able to know that this is a normal distribution. This normal distribution isn't because we're assuming it, it's coming from the central limit theorem. That's what makes it powerful. Then we can make probabilistic claims about the tails. And then we can do all of our hypothesis testing, both on the sample means, but also on the sample slopes. So that's my 10-minute recap of how we do inference, which we're going to come back to later today. All right. So that's the econometric model, really the foundation of everything in econometrics in 5 minutes. So we can actually simulate this stuff, and that's what we did in the notebook. We said we want to check in finite sample whether this is actually true, whether it's actually unbiased, whether the distribution of sample parameters is actually centered on the true population parameter. That's the unbiasedness. Then we also want to talk about precision. So the central limit theorem also tells us how the shape changes as our sample size increases. So we just wanted to check whether the shape actually follows that, whether the shape in finite sample follows the prediction in the asymptotic sample. And then we thought about the t-tests, so checking the tails, and then using confidence intervals, checking for the type 1 error. So we were essentially simulating a test of all of these sort of main properties of the central limit theorem. Okay, so we're not going to do it again, but this was the picture. We built a model, ran a line through it. We even had non-normal errors. So in reality, the underlying data generating process had very little to do with the normal distribution, or at least the error terms were not normal. And it still turns out that the shape of the distribution is normal by the central limit theorem. So that's what we did here. We just ran a little Monte Carlo. It turned out, even though the error terms were not normal, the distribution of sample slopes, so this beta 1 estimate is exactly this picture. This is the prediction. This is the actual distribution of 10,000 observations. and it looks like it matches in shape the prediction by the central limit theorem. This is not a sample size of 10,000. This is two different sample sizes, 25 and 100. We're just doing both of them 10,000 times. So we have small samples, but we've done many of them and plotted a slope for each. Okay, so this is nice. It shows us that we get the precision. Is this distracting to have Maxine on the side here? Sometimes I forget the picture's there, and sometimes I notice it and get a little jolt of comfort. I also get jolts of comfort when I see this the result with the central limit theorem. But that's a personal problem. So then we actually used our knowledge about the standard error to set up the actual shapes of the distributions. So nice. We're not going to talk so much about this. But then we also checked that our level of confidence was about right. But even here, this is also a Monte Carlo, and you can see, even though we've taken 10,000 observations, the actual type 1 error rate is still not exact, right? We still don't even have 2 decimal places approximated correctly. So again, just a note about the convergence of Monte Carlos. All right, so the last thing we did last class was actually build this more sophisticated simulation of the Electoral College. I had some conversations about the Electoral College in my office. If you're not familiar with the Electoral College, like not from the US, or you don't pay attention to politics, that's A-okay. This is just, I've spent a lot of time thinking about these things, so I think this is, for me anyway, a nice example. So what we walked through was first a setup using independent states. So if we have polling data historically, and what we can do is try to predict the outcome of the election using polls. So our X variable behind the scenes, we're not actually running this, but the economist has run this, where we have polling data, so polling, where we have the Democrat on one side and the Republican on the other. And this goes from 0 to 1. So I'm not actually writing numbers here, but this is just, on one side it leans more Republican, and on one side it leans more Democrat, and in the middle it's 50-50. This is for polling, and then we use polling to make predictions about the outcome. This is the actual election. So again, we have a scale going from Republican to Democrat with 50 in the middle, and this is the election directly. This gives us data, right? So we can do polling right before an election, and then we can use that to make predictions using historical data about the relationship between polling and how elections go. So the picture looks, something like this, probably positively sloped. I don't know the details of how The Economist actually builds these models. I imagine they're not linear, but let's say they are. This is highly stylized, but something that looks like this. We're trying to predict polling outcomes election outcomes using polls. So then we can make predictions about who's going to win an election using polling directly. So we can just take our current polling, so this is in 2020, and then just plug this in to the model to give us our prediction. So this is all the background for where these numbers come from. And what we're saying is not that, the prediction is a probability about who wins. This simple model here is just using the model to predict the outcome of the vote directly. So the economist did something extra to make probability claims about who wins. But that's the data. And then here, this is just the electoral votes. So how many votes each state has in 2020. It changes a little bit depending on the year, using census records. So larger states contribute more and smaller states contribute less. And in general, this is winner take all. There are 2 states, Nebraska and Maine, that don't do winner take all, but all the others, I believe, do winner take all. Alaska, anyone know, is Alaska winner take all? Okay.
I think they only have 3 electoral votes.
Yeah, so
Who cares?
who cares? Yeah, exactly. Yeah. Unfortunately. Yeah, we should do a national popular vote. Okay, so yeah, too reasonable.
No.
Yeah, that's not why. Okay, so this is just the distribution of Democratic win probabilities. We could do this with Republican win probabilities, where we just take 1 minus this. But these are just coming from the statistical model the economist built. And then we just ran the simulation. So I'm actually going to rerun this because we have one more thing to do. So this is just one draw, and it turns out the Democrat gets almost 400 electoral votes in that simulation. But we can keep running this, and like we said before, each time we run it, it gives us a different number. So what we did here is we just ran this 100,000 times. And the Democrat won in almost all of them. This was just a visualization of those runs. So this is a histogram. So we're just going through and counting using bins how many elections fell into each one of these Democratic electoral vote outcomes. And you can see, I think there's only one that fell outside somewhere in here. And when we look at this, we think this is probably not that realistic. We talked about part of the reason this doesn't capture the reality of the messiness of the world. And part of it was due to common shocks. So even if we do predict the outcome correctly using this statistical model, we have to account for correlations between state outcomes. So even if the individual state level is very predictive, when we're thinking about the national level, there are strong correlations between the ways different states go. So what I did here is talk through a more sophisticated model. We don't have to know all the details of this specific model. The details here aren't general. It's very specific to this kind of modeling. But what we want to do is essentially convert from a probability. Here's the problem. We need to add a common shock to every probability. So we want to move the probabilities in a correlated way. And if we were to just add some shock to each of the probabilities, this would not give us, it'd be hard to, we could do it, and then we could post-standardize. But the better approach is to convert from a probability to, which is on the 0 to 1, to a real number, which is on the real number line. Shock the real number, and then convert back to a probability. So that's essentially all that's happening here. You convert using log odds into an alpha, and then we shock that, and then we convert back to a probability. So that's all that's going on here. I've just implemented this in Python. So we walked through different common shocks. So this is a common shock of 8, which is a strong shift against the Democrat. I'm sorry. This is the range of the common shocks. And when we introduce additional error, so we're essentially going from almost every election the Democrat wins to making it more like a coin toss. And as we do that, we get closer and closer to 50%. So this is just saying, even though it's centered on 0, we're moving towards more of a coin toss. So centered on 0 just means coin toss, equally fair for both parties. And as we move towards the coin toss, we get closer and closer to 50. So then I just visualize this. This is, looking at different common shocks and sort of showing exactly what you'd expect. When the common shock leans towards the Republican, the average Democratic electoral vote tends to go down. And when it leans towards the Democrat, we get even more Democratic outcomes. Okay, so then I did a couple of extra things here with comparing correlation structures. But the last thing, I think we had 5 more minutes in class. We could have just done this. That's why we're taking 10-minute breaks from now on. We're going to perform a counterfactual. Oh, we already did this. I'm sorry. This is just, we whipped through this, but this was the original, let's see. So this was just shifting everything down by 4. So we're moving alpha in the direction of the Republican by 4, just entirely across the board. And then we run the elections in that case. So it's closer to a 50-50. So instead of using a probabilistic shock, here we're just deterministically shifting the entire election. So instead of drawing from a distribution, we're just shifting it exactly by 4. Where before, this alpha shift was a random shock. So before we had randomness in the shock and randomness in the outcome of the election. Here we just have randomness in the outcome of the election after we've shifted it. So this is giving us one particular value of common shocks. We're saying, let's just look at this one. So it's close to 50-50. We're just gonna run that. Okay, and this is just the distribution of electoral votes, and you can see we've taken some of this cluster and shifted it down. So everything's just been moved down by a bit. Okay, any questions here? Finally, the last thing we're going to do in this notebook, there's one extra example if you're interested in sports. This is a historical example from before I taught the class. So not particularly interesting to me, but if you're interested in sports, I have it all written out in Python for you to take a look at if you like. The last thing we're going to do is just look at what happens instead of flipping every state. What if we just flipped one? How would that change the outcome? So Texas is, I believe, the second largest electoral votes, 7% of the National Electoral College. And one question we might have is, what happens if we were to lean it towards the Democrat? So we're going to set the alpha for Texas specifically. So we're not going to use a national shock, and it's not going to be probabilistic. We're going to perform a counterfactual. What happens if we were to move Texas on its own? So I'm just going to run this. Let's see, where's stateless defined? Here. So state list is just a list of all the states, and we're going to update the Texas alpha to be 4. Okay, so the original Texas alpha was negative, so this was a state that leans towards the Republican Party. But what we're doing by shifting it by 4 is not assigning it to be 4, but we're moving it from this number to this number. Okay. So then all we're going to do from here, we just have our alphas, and we're going to just run with the Texas shifted. So this is just, Texas alphas are just all of the alphas just with Texas shifted. So when we run this, we get these numbers. So this is the win probability originally with the alphas that we generated, and then here we have the post lean. So just moving Texas around, what happens to our probabilities. The nuances here aren't particularly important. What I'm trying to communicate is that simulation gives us, if we set up our simulation correctly, or in the ways that we wished, and we have like almost full control over these things, we can perform any type of counterfactual we're interested in, right? Like, this is just a model. I have full control over the model, and what Monte Carlo gives us the ability to do is tune any parameter we like. So that's what I've done here. I've moved the win rate around, and what this does is shifting the alpha by 4 gives us an increase of like 0.4%. So it's not a huge change, because we're not looking at a change in the national level. What we're doing is changing just the one state. And even though it's very important, it seems to not impact the outcome so much directly. But this is meaningful for sure. All right. And then every time we run this, it looks slightly different. Any questions here? Anyone into soccer? There's a T-bar by my house, and they play lots of soccer. The owner is like a huge soccer fan, so whenever I go, he talks to me about soccer. Even though I've told him so many times I don't watch it very often. Every 4 years, that's how often I watch it. Okay. So the next thing we're going to talk about is interesting. This is not, the screen is not updating. Sorry for those two of you who are out for the screen. Okay, so the second thing we're going to do today is talk about nonlinear regression and what we call quantile regression. These are, so we briefly covered some of the ideas for the workhorse models in econometrics.
Did you just start Jupyter Lab without Anaconda, or do you have Anaconda?
I have Anaconda installed.
Okay.
Yeah. Anaconda is the way I run Python. Yeah.
Is there a way to run Jupyter Lab without Anaconda? Because I hate having two icons on my dock.
Two icons on your, you mean down here?
Yeah.
I think you can just remove, oh, you mean like when you open it?
Yeah, because you have to like open Anaconda first and then open Jupyter.
So I might have changed the default app to run, because like when I click on this, it just opens directly in Jupyter Lab.
Okay.
So maybe like a default app setting. I actually don't remember. It's been a while. But yeah, this is an Anaconda distribution. Yeah, and I can just click on the file and open it. So what we're doing, and feel free to just like interrupt me with questions. Interrupting most of the time is rude, but I think in this class, I would take it as a compliment if you did. Okay, so what we're doing today is changing two assumptions that we typically use with our main workhorse econometrics model. you've talked about ordinary least squares or regression or general linear model. What we're doing today is relaxing two of the commitments we've had to make to run OLS. The first one is that the relationships between our variables are linear. So whenever we add a new term, it's going to be a linear addition to this equation. So all of the terms are linear. Even if we have polynomial terms, we can add like an x squared. That's still part of the general linear model, or regression. I usually call it general linear model as the more general term. So we can do polynomial regressions just fine. The commitment is that the terms are additive. And the second commitment we've made is that we're estimating a conditional mean. So it's the expected value of y given x. What we're going to do in this notebook is relax these two constraints. How many of you have seen any of this before? Nonlinear regression? That's nice. I think a lot of this will feel, if I'm doing my job correctly, a lot of this will feel like pretty natural as an extension of what you're already familiar with. But it's good. Yeah, it's sort of nice for me that you haven't seen this before. Did my explanation here feel familiar? Okay. I think sometimes, like in econometrics classes, this is not a knock on any econometrics class. Getting into the weeds is really important, but sometimes it's easy to lose sight of the higher level ideas, which are these. So in the middle of all of that like matrix multiplication you were probably doing, this is what's going on behind the scenes. These are the high level ideas. And those are going to apply in a similar way, in a certain kind of way to what we're doing today. Okay, so the first thing we're going to cover is what we call nonlinear least squares, which, is this too small? Probably. Let's do this in Jupyter. So nonlinear least squares, essentially, it allows us to do more complicated things. So the assumption we're going to relax with nonlinear least squares is just that we have an additive term. So we're just going to, what nonlinear least squares does is it allows us to make more general functions. So this is a function, and what nonlinear least squares does is allows us to generalize that. So with OLS, this is our y value is equal to some function which takes in the data and the parameters. So this is, our x is our data, and it takes in the model parameters plus some epsilon. The specific functional form is, beta 0 plus beta 1 times x1 plus beta 2 times x2, and so on. But with nonlinear least squares, we're not going to make, this is the assumption for ordinary least squares. Nonlinear least squares allows us to do any function. So this is y is equal to f of our data, and then our parameters can be anything. The only assumption is that we have an additive error term. Okay, so we're still targeting the expected expected mean, so that the expectation of the data. But all we're doing is saying, let's not require that it be this specific function. Today we're going to talk about a logistic growth curve, but there are lots of others. So people use lots of different varieties of this thing. Quantile regression sort of changes this a little bit. Instead of removing the linearity assumption, what quantile regression does is it changes the way we calculate errors. So typically we've calculated errors using the mean squared error. So we square the difference between the model and the data, and we treat that as our error. What we're going to do with quantile regression is use something that's less nice mathematically, but gives us some additional power to look at quantiles instead of means. But we're going to keep the linear component. Okay, any questions here? So we're going to sort of, in some ways, come full circle. One of the particular nice thing about OLS, among others, is that we can take a first derivative because the error is this nice quadratic, like, square term. We can take the derivative and minimize the error term, getting a solution in closed form. It turns out it's just this thing. You've seen this before in your econometrics class, just a bunch of matrix multiplication, which gives us our betas. So we don't actually have to do any optimization because we've done it mathematically. We can just multiply matrices together, and it gives us our betas. When we go to nonlinear least squares and some other approaches, we can't compute an equivalent solution in the same way. It becomes, in general, much, much harder, which means we have to do some numerical optimization. So this is where we turn back to our topic 2 concepts. So we're going to use numerical optimization again. So this is where we're going. The first part of this, we're going to talk about nonlinear least squares, set up the objective function. We're going to model Twitter's user growth. So this is from when Twitter was called Twitter. I'm not a social media user, so I don't, this is just a great example. We're going to talk about starting values. We're going to use derivatives to calculate standard errors. So when we're in this environment, standard errors become very easy to compute because we can just compute them directly. When we, taking a derivative of this thing gives us some nice structure. We can still use standard errors for inference. We just have to compute them numerically, which is not a real problem. I'm gonna show you an example of where of some of the limitations of nonlinear least squares. One of the things we have to do is commit to a particular functional form for the function. So we're going to make claims about this function. And if the function we pick isn't the right one, then we run into some problems. So I'm going to show you an example of Snapchat data. We're going to use the same model we built with Twitter data, and I'm going to show you that we encounter some problems. We're going to show some examples where we don't actually need nonlinear least squares. To do linear, we can use a linear model to do to estimate a model that is inherently nonlinear in some ways. So we're going to do what we call linearize a nonlinear model. Which, do you all love Cobb-Douglas? There's a nice reason we use Cobb-Douglas because it is linearizable, or that's one of the reasons it's nice. You remember, in your theory classes, you would take a log of Cobb-Douglas, which turns it from this product into additions of log values. that's linearization. So if you do that, you can then estimate the parameters, the alpha and beta of the exponents are the model parameters in estimation. Okay, so that's the first part. We'll see how far we get today. I seem to be going more slowly than I expected. Part 2 is quantile regression. So instead of looking at like a squared loss function, we're going to use a particular kind of, it's like a modified absolute deviation loss function. So instead of squaring it, which makes extreme values incredibly impactful on the estimate, we use a absolute deviation value, which looks like a V. So then error terms in both directions are treated the same in a specific case, but then the extreme values don't overweight the estimate. And then we're going to look at Pittsburgh house values. Okay, any questions here? This is the roadmap. This is where we're going. We're going to start with nonlinear least squares. This is the setup. I've already sort of explained a lot of this. Fundamentally, it's a pretty simple idea. If you're familiar with econometrics and all of the basic apparatus, this is not fundamentally that different. The only difference is that we don't have a nice linear function, which the linear function makes it easy to do lots of things because it's easy to take derivatives of. But in general, we can use any function, and that means all the nice results we had don't necessarily apply. We still have this result, though, which is that the expectation of y given x is just the evaluation of the function. And we're going to say this function f has j unknown parameters. And what we're trying to do is just estimate them. The way we pick the model, so like there are lots of models we could write down, but the one we pick is the one that minimizes the sum of squared residuals, or sum of squared errors, where we just take the sum of the difference, the sum of the squared difference between the data point and the model prediction. And then we take all of this and try to minimize it. So we pick the betas that attempt to minimize. The way we classically solve this in OLS is, you've probably done this proof, right? Is if this is a linear function, we can just take the first derivative and solve for first order conditions for betas. That's very nice. We can't do that in general in this case. So that's the fundamental challenge. Okay, so let's just get into an example. So we're trying to model, this is a time series model essentially. So there are some problems with using time series with OLS. The main one is autocorrelation. So you have to think about these problems carefully. I'm teaching the intro data class for the undergraduate major, and we're about to talk about autocorrelation today. So I was just thinking about that for this problem, but we're going to do it anyway. The classic growth curve looks like this. So this S curve, you've probably seen it before. We start slowly, so we get this slow rise. It speeds up in the middle, and then it kind of tapers out as we reach saturation. I have a bunch of data we're going to use to actually model this. So this is coming from public filings. So I have a bunch of years, I have quarters, we have active users in the US. And then I just have a time period value. If you wanted to look at the first ones, so you could do header. The time starts at 1 and then runs as long as the data. So we have 37 observations. Okay, so nice. this is just a figure of the data. You can see this here. So this is just over this time. This is not the beginning of Twitter, but this is the beginning of our data. We're going to actually use our model to extrapolate earlier before our data set later. But you can see we have like a sharp rise in the middle, and then we get this like flattening out as Twitter starts to reach saturation. Or maybe other reasons. For whatever reason, it's flattening out after a steep rise in the middle. We could fit whatever curve we wanted to this data set. But the thing we're going to use is the logistic curve. That looks like this. So let me just talk you through the parameters, and then I'm going to show you a figure. You've all probably seen this before, right? How many of you have seen this? Okay, so maybe we'll talk through some of the details in more detail. We could use a polynomial, right? So if we're looking at this, we could say, well, it looks like there's some curvature here. So a line, like a linear relationship, is probably not appropriate. But we could add a polynomial term. So like time squared, which would allow us to get some curvature. We could even include like a cubic. So we could have whatever polynomials we like. Just some way of getting some curvature while still remaining in the general linear model, or the regression framework. But let's do something a little more specific. When we think about the data generating process, we're going to make a guess about what the function actually is. So instead of just trying to approximate the function using a linear relationship, like additive in terms, what if we actually use something that might model exponential growth more directly? This function is used, have you done like logit models? So it's used in logit. It's used in the exponential growth of cells in a petri dish. So cells, like you're in a petri dish, cells will, there's like a bunch of food in the petri dish and a bunch of room. Cells will like split. So like a bacteria or whatever being grown in a petri dish, it will split. So it's doubling for a while. And with exponential growth, the doubling happens really, like happens slowly, but then it speeds up. When you're in a petri dish, though, we hit sort of capacity constraints. So eventually, like we can't keep growing forever, eventually we'll hit a maximum. So we get this slow takeoff, a rapid increase, and then we hit our sort of carrying capacity. So this is used pretty widely in the sciences. The logistic growth. I think early large language models in deep learning used the logit. I think they use a different function now that's easier to run, but this is a nice little function. The alpha term is the ceiling, so this is like where the carrying capacity is. You can see this because if you take the limit as time goes to infinity, this term goes to the exponential goes to 0, and then we're multiplying 0 times the gamma parameter. So then all we're left with in the denominator is 1. So it's 1 over alpha as time goes to infinity. Then gamma essentially controls where we start. So if we start at time 0, we plug in 0 for time. This thing goes to 1, so it's e to the 0, so that's 1. So we have, at time 0, we have alpha over 1 plus gamma. So gamma is sort of how we control the starting position. And then lambda is essentially the slope. So it's how fast we grow as time goes forward. So these three parameters allow us to control the shape of this relationship. So this is just one example. We can do lots and lots of different ones, but this is a picture of the function. And this is really nice. We use this in logistic, or logistic regressions. We use this, to model populations in with finite carrying capacities, and lots of other different areas. It's a really powerful, specific function. Any questions here? Yeah.
Carrying capacity just means this is the ceiling.
Yeah, so like in the Petri dish, it's like you can't grow beyond a certain capacity, and the carrying capacity is just the maximum population. Okay, nice. So this is what we call the S-curve, if you've heard of that. Slow initial growth, rapid acceleration in the middle, and then we sort of have this leveling off as we hit our ceiling. Okay, so the way we can write this in our nonlinear regression framework is something like this. So we have our input t, and then we have three parameters. So our essentially the equivalent of betas in the OLS are these three parameters: alpha, gamma, and lambda. And it's going to look like this. We're going to do exactly the same thing we've done in the past, right? So every time you've seen I don't want to make assumptions, but in general, the thing we do for error is we look at the model, we take the difference between the model and the data, square that, and then find the sum of squared errors. Or we can talk about mean squared error, which just allows us to normalize for the size of our sample. So this is the thing. And then what we're trying to do is just estimate the beta. So estimate the sample statistics. Or these are the estimates for the model. So just like we talked about in O2, the place we start can matter. So our initial guess, so because we can't perform a general optimizer, we need to think about our initial guess and then perform like our standard gradient descent or similar approaches. Today we're going to use actually Neller-Mead instead of Newton-Raphson, but the general idea is the same. We're trying to find the landscape, and we don't know the entire landscape, so we're going to kind of move locally around the landscape. Okay. Turns out we can use the structure itself to give us some initial calibration, and then we're going to actually perform the optimization after we do the calibration. So this is my sum of squared residuals using the logistic function. So I have three parameters. I'm going to call these params. This is the prediction. So this is just the function itself, but I'm giving it the data, so Twitter data, for using the predictor variable. So like I talked about with the data itself, we have this variable t. So t is our main predictor variable. This is just telling us what time we are on the horizontal axis, and then we're going to try to predict Twitter active users in the US. So this is our x, and this is our y. So we plug in t for our time, and then we get a predicted value. The residuals are just the difference between the Twitter active users and the predictions. And then all we're going to do is square the residuals, as we always do, to get the sum of squared errors. We're using sum of squared errors here. We could use mean squared error, but our sample size isn't going to change between different model specifications, so it doesn't actually matter whether we use mean squared error or sum of squared residuals. Okay, so when I run this, I get this thing. So the sum of squared residuals at some initial guess is, so I'm just guessing these numbers right now, but we'll actually do some a better guess in a second. It gives us this. So this is a function that just takes in the data we have, runs it through the function that we're using, and then spits out how wrong that model is, given the parameters. So I give it the parameters and the data, and it tells me how wrong I am. This is the objective function. We're trying to minimize this. Okay, any questions here? So like I mentioned, we're actually not going to use Newton-Raphson. We're going to use Nelder-Mead. I think I mentioned this briefly in topic 2. Nelder-Mead, as I understand it, works better than Newton-Raphson when we're in higher dimensions. So more than like 2, I think. Nelder-Mead is a little bit better. Here we have 3 dimensions. It essentially performs the same kind of approach as Newton-Raphson, like trying to like fall down a hill. It just does it in a slightly different way. I think I showed you that picture of like, there's like the triangle that was kind of like flopping around. That's Nelder-Mead. And that's about the limit of what we need to understand about it. It performs generally better in higher dimensions using that simplex method. It allows it to sort of like not run into asymptotes. You can sort of think like, because of the higher dimensional structure of the simplex on the space, it doesn't run into the asymptotes quite as often. Okay, so we're going to try to, so we made this little guess here for the different values, alpha, gamma, lambda. What we want to do, though, is be a little bit better. We want to try to, you remember, picking our initial guess can impact the outcome of the optimization. So if we can pick a guess that's very close to the truth initially, we can at least give us a better chance of being in the ballpark. So what I'm going to do is try to make a case for how I would pick alpha, gamma, and lambda. So we're going to try to pick alpha 0. So thinking back to the function, let me maybe put this on the board. So we have this function, and I'm just going to draw in both the function and the data. So this is time on the horizontal axis and users on the vertical. The function itself looks something like this. And we have some data points, and let's make it really nice for visualization purposes. The question is, where do we pick our alpha? So this is f is equal to alpha over 1 plus gamma e to the negative lambda t. So if we're trying to pick alpha, we want to think about, alpha is essentially the asymptote. So we want to pick a value that gets us really, really close to the asymptote without doing any like optimization yet, just thinking about where we pick our initial guess. So if I'm doing this, I want to think about the long run. So I'm going to try to pick maybe the last value, or maybe a value that looks like it might be the asymptote. In this case, it's actually not that hard to see this. You can see the last few values here don't seem to be moving that much. So it looks like we've already peaked in like right before COVID. So I'm just going to use one of those numbers. It's going to get us pretty close. It's not perfect, but it's going to get us close as an initial guess. So that's why I'm picking 68. 68 million is about where it starts leveling off. So that's going to be my initial guess. So 69 maybe. And then for gamma, we have to do a little bit more work here. Gamma is how we calibrate the zero. So we look at the function, we evaluate it at time is equal to 0. And if we evaluate this at f of 0, this gives us alpha over 1 plus gamma. So if we know the Twitter users at 0, we can then use alpha, the Twitter numbers, and then solve for gamma. So it's not quite as simple as the way it was with alpha, but we have all the information we need to solve for gamma. So this is just me writing it out. So f of 0 is that thing. It looked like, maybe at time 0 we had 9 million, and then we just plug all these numbers in and solve for this. We've already guessed for alpha 0, so we can just plug that in as well. The first values are like 10. It's increasing around that time, so we'll just go under. Any questions here? So I'm going to set gamma equal to alpha 0 over 9, and then we subtract 1, which gives us this. Okay, the last calibration we need to do is for the lambda. So this is like the rate of increase of the function. So it's this thing. So essentially, like how quickly we go from 0 to alpha. There's a bit of math here that I'm going to skip over, but if you're thinking about like the maximum rate of increase, you can think about like where it's like the maximum first derivative. So we maximize the first derivative to find the fastest slope, which is the like the second order. It's the second derivative. We set it equal to 0. So we maximize the first derivative by performing an optimization on the first derivative, which means we take the second derivative and set it equal to 0. When we do that and then take a log, we get essentially this thing. I'm going to skip all the steps. It's not that important. But this is how we can sort of get at the calibration of lambda. So all I'm going to do is set lambda equal to this. We know gamma, so we can just plug in gamma in for the log. This is how I would write it out. So we know gamma guess. We're just going to take the log of gamma and then divide it by 10, which was our time. So you can see it looks like it's going fastest right around time 10. You could use different values here, but that's at least a reasonable approximation. Okay, any questions here?
You're choosing the approximations based on what you see on the graph.
That's right. So it's just, I don't know exactly what the function is. That's what we're going to do with the optimization. But like with all of the Newton-Raphson things we did, it's good to get a guess that's as close as possible to the final outcome, even if it's not, this is not an exact value. That's what the optimization will do, but this at least gets us in the ballpark. I think with this one, you could probably just arbitrarily guess and it would do pretty well. But we don't know that for sure, so that's why we're doing this. Yeah, good question. Any others? So let's run this estimation and then should we take what's today, a 13-minute break? Titrating down to 0. By the end of the semester, we'll take 0-minute breaks. And then if we were to run this into the summer, maybe we'd take negative breaks where,
We're going until 11:35.
yeah, I continue adding time on the end. Okay, so like we just talked about, right, like these are not precise values. This is just me eyeballing the thing and trying to approximate a good guess. What we want to do is actually run an optimizer. And thankfully, we have all the machinery to do this. So we could use SciPy optimize. So this is just the minimize. I'm giving it the objective function. So this is the sum of squared residuals, which is the thing we defined earlier. So I walked you through, like we have the logistic function. We're putting in the time values, and then we're checking it against the Twitter users directly. And then here we're using our guesses. So we just walked through and constructed alpha 0, gamma 0, and lambda 0 as our initial guesses for the function. So you can go back and look at the specifics for how the function is defined, but minimize is just giving the initial guesses using this parameter set. And then we're defining a method. So I think this defaults to Newton-Raphson if you don't define it. What I'm doing here, because we're in higher dimensions, it's, as I understand it, best practice to use Nelder-Mead for these higher dimensional problems, because it gets stuck less. So then it's going to spit out a result. If I run this, we can then actually extract the results. So this is result, and then I think if you, let's see, I think if you just plot out result, it gives you all of these things. But what we want is actually just the parameter values themselves. So that's what we're getting here, and I've just packaged this in a way that's easy to read. So we have alpha equal to alpha hat. So this is our, we've used our initial guesses to start, then we've optimized, and this spits out the answers, the best fits. Okay, and you can see our initial guess for alpha was 69. Our initial guess for gamma was like 6.6, and then our initial guess for lambda was like 1.9. So roughly 1.9. And it turns out most of that was pretty close. The alpha was close. The gamma was a little bit further away, and then lambda was, I think it was that pretty far away? So anyway, this is the optimized, parameter values. The amazing thing with what we've done here is we're not relying on any optimization result like we do in OLS. This is just using numerical optimization on a generic function to give us a model fit using that nonlinear function over parameter values. So I mean, this is a really powerful kind of thing to do if you think your data isn't, like the underlying process is truly not a linear function. So let me just plot the residuals. So this is the standard error, and then this is the prediction at time 100. So we're making a prediction beyond the short term. So I'm going to show you the fit really quick, and then we'll take a break, and we'll come back and talk about some of the nuances. So this is just the picture of the data and the model. And can I get a round of applause? No, don't clap. Please, actually don't. It's annoying. So I think this looks pretty nice. Amazing, actually. So if you suspect that your data is drawn from an underlying population that is a population relationship that is not linear, sometimes these things are going to just work a lot better. So when we come back, I'm going to show you an example of bad calibration. We're also going to talk about predictions outside of sample. And I think we're not going to get to quantile regression today, but we'll see. 13 minutes takes us to 10:34. If I can do math, I can at least write a computer to do math, so that's a plus.
Do you want to just meet in the lobby again?
Yeah,
Okay.
I'm gonna stay after.
Oh,
today.
okay.
Recently you were launching the Jupyter without Anaconda.
I was asking Taylor if he knew how to do that. I don't know how to do it.
Now you launch every time you launch Jupyter.
Yeah, so you have to go into Anaconda here and then launch Jupyter.
Have you ever tried do terminal?
No. No.
No, if you shut Anaconda.
Because it did this.
Okay, okay.
This time. So you just like open a new terminal window and then type something in here.
Won't you close everything up? So you
Okay. I don't want to close it right now because
Oh no, okay. You can actually like in the terminal and just type Jupyter notebook and it should open.
Okay. I'll try that then. Thank you.
Jupyter space notebook and just type that and it should open like it's like a local server.
Okay. Perfect. Thank you.
Sure.
Yeah.
I know that you're not so constructive. Like, you could do it also, like, if they wanted. No, it's like, yeah, no, cool.
So what are they saying? I actually appreciated it. That's what I think it seemed like they were trying to lean into it. Because that's what the future is going to be. Maybe they're like, maybe give me to like have a strong career. Focus. Yeah, it's just all those using YouTube. Yeah. No, but I think like I love the way they like prompted us to use AI was helpful. Okay. Cool.
And it's just like so depressing every time I come in this thing, it's just like, yeah, like, you just can't really like be picky about like protect your
You gotta take what you get.
and then like, yeah, like she has to watch coworker dynamics and like, yeah, I when you see your coworkers more than your friends, you have to like, this is so, every time I join one of those, I'm like, this is just making me think I'm like in a completely wrong place.
Yeah.
Like everything is so depressing, like.
I'm talking to my cousin tomorrow about what's it called? He works on what he worked on now for like 10 years. And I'm like, we're talking to him about like how to approach like applying for jobs later on, like using connections to like work in a place that like is actually interesting to me. I'm kind of worried that he's gonna like douse my hopes a little bit. I'm disappointed.
It's so nice to actually have
I'm
the
glad
rejection.
I'm going to cruise. Like that's what I want to do. I want to look at those trailers.
I like love to try to apply to a lot of like cruise companies, like to work like in their corporate. Oh my god, I just have the locations and
No, I mean, if I can't find a job, I'm gonna be like one of those people who works on a yacht.
I'll probably throw it down.
Yeah. It's nice to meet you. It's nice to meet you.
Just like it's
Yeah, we get to become gods in the machine. That's the prize.
Anyone want to do some work? Well, here's a cute picture we've already seen. Did I tell you this was yesterday? Max loves these mango slices. We live really close to an Aldi, and you can just walk in, buy these like pre-cut mango slices, which are perfect for her to just hold in her hand and stick in her mouth. So we'll like walk around and eat fruit. This has nothing to do with fitting nonlinear models. So before break, we built this thing. This is just a visualization of the data and the model, and you can see we get really, really close. So the rest of what we're going to do in the next hour is talk through some of the ways this breaks down. So like to think about the problems we can run into when doing these things. What we've done so far is think through like an idea about what the functional form should look like. This wasn't just looking at the data, but it was also thinking about the data generating process. So we have to be pretty specific about what we expect the data generating process to be. We're going to talk more about this with maximum likelihood estimation in a couple of classes. But this is a good place to start doing that kind of thing. So thinking about how the data is generating, not simply taking a line to a scatter plot, right? We want to think about the underlying process itself. This is the actual model, right? We went through, we visualized the curve and the data, but if we're looking at the model itself, we can actually plug in the coefficient values into the nonlinear function. So nice. The ceiling we said was just over 68, which is pretty close to our guess. And then the growth rate parameter tells us how quickly we go from 0 to saturation. And then this just tells us kind of the starting place. Okay, so that's nice. The next thing we're going to talk about is how we make inference. So what we've done so far is just build the model itself, which is the process of, for analogy here, it's the process of picking the beta 0 and beta 1 parameters of our linear model. But what we actually want is to make claims about the underlying population, which is the entire motivation for inference. Inference is going from our data, which is just one observation or one sample. Every time we redraw the sample, we get a slightly different collection of data. So if Twitter was founded by a slightly different person, but in a very similar way, we would get different user growth. Every time we draw our data set, we get a different value. These are all drawn from an underlying population that we would wish to make claims about. So this observation, this sample, may be one that's drawn here. So it could be something that's not exactly equal to the population mean. And our question is about making claims about the population mean, which we will never observe. All we have to go off is our sample. This is inference, right? We want to make claims about a thing we don't see using something that we do, and we can make probabilistic claims about the truth using what we do see. To do this, we have to think about this distribution, so the shape of the central limit theorem, the shape of the sampling distribution given to us by the central limit theorem. The amazing thing about the central limit theorem is we actually don't need to necessarily know the underlying generating process. What we need, though, are standard errors. So in nonlinear least squares, what we do is construct what we call the Jacobian. Have you seen the Jacobian before? Okay, so when I first saw this, I was a little terrified. This is really just a fancy way of talking about a matrix of partial derivatives. We use it in statistics. There's probably other areas we use this as well. But let's just talk through some of the details here. There's a very nice analogy to how we construct standard errors in OLS. This is really just doing a very similar thing to what we've done in OLS, just using sort of our approximated values. Okay, so the Jacobian is just a matrix of partial derivatives. So we have J parameters and K observations. So you can see I've so this G is just the Jacobian matrix, and this is just telling us row and columns. And what we're doing here is we're taking a derivative of the function itself. So this is this function, so the nonlinear least squares function, which in our case is the logistic function. So we're taking a derivative of the logistic function with respect to each of the parameters. In our case, we have 3 parameters. We have alpha, gamma, and lambda. So we're taking a derivative with respect to each one of our observations. So at each one of our observations on the horizontal axis. So this is, we're going to plug in our x0, and we're going to find the slope with respect to each one of these. So it's not the slope of users, it's the slope with respect to each one of these parameters. But we're doing it at specific values on the function. So then we just do this for each one of the data points we have. Okay, so this is the Jacobian. Weirdly, this is kind of important for how we construct confidence intervals, or standard errors, and then use the standard errors to make inference. This is the shape. So it's like we have this huge matrix of, it's like the size of the data set times the number of parameters. Just a huge matrix of partial derivatives. So nice. Any questions here? Yeah.
The next, can't read the subs.
Oh, just 0. It doesn't actually matter. Just indicating that it's one of the data points. You could say J might be more appropriate. Okay, so if you remember back to OLS when we were constructing like variance, the variance of the model, what we're doing is we're using the true parameter, or sorry, our estimated value, the estimated variance from the data. We're multiplying that by the product of two of our X being our data set. We're multiplying the data matrices, transpose or prime times X, and then we invert it. So X transpose X, but inverted, and we multiply all of that by the estimated variance in the data. So this is, you can't read this as hat, but this is sigma hat X squared. Sorry, sigma hat squared. So this is sigma hat, and then we square it. So nice. So this is this is what we do in OLS, right? So this is how we get the variance of the model which is essentially our standard error. X is just the matrix of observations, which if you're taking the derivative of this, our OLS function, with respect to the parameter value, that just gives you back, because it's a linear model, that's just going to give you back the data. So in the linear case, the derivative of the function with respect to the parameter is just the data. So in our case, the with OLS, G is just equal to X. Any questions about this? This is I'm making an analogy here, going from what we're familiar with to something that's a little less familiar. So let's see. The derivative, let me just write this on the board. The derivative, so our GJK, the derivative of f with respect to the parameter beta k at our xj, this thing in OLS is just the observation xj. This is in OLS, but the only reason this works is because it's a linear model. In nonlinear least squares, we don't have this direct relationship. We have to do something a little bit more fancy. We can't evaluate it directly. So all we're doing is essentially replacing the OLS version with our new version, which is just the Jacobian, which is just essentially the slope of the model, like how the model changes in slight increments around the data point if we were to subtly change the parameter values. That's what we're doing with this Jacobian. That's the intuition for what it's doing. It looks, I mean, it's this like massive, scary little thing, but fundamentally that's what it's doing. Just essentially replacing the data in our standard error calculation with something that we can compute using a computer. I've gotten so worked up, I've gotten marker everywhere. Any questions about this? That's how I understand what the Jacobian is doing, replacing the data in the standard error calculation. Okay, so nice. And this, the standard error is just telling us essentially how spread out the sampling distribution is under the central limit theorem. Okay, there's a little bit more here. This is just the intuition I just walked you through. I just wrote this out just to give you some sense of where this is coming from and why it matters. We need this to be able to construct the standard error, which then allows us to give us, it allows us to find the spread of the sampling distribution, which then allows us to make claims about the tails. So that's the big picture and why the Jacobian matters in this case. Okay. We could do this manually. I was going to write out some code here to do it, but I think we'll not, because we have computers to do this for us, or pre-built packages that run computers to do this for us. So what we're going to do instead is use SciPy optimized curve fit to make predictions. Okay, so nice. This is the function we'll use, curve fit. I wrote out this SSR function before, which like explicitly defined the function and then the objective function, which was the sum of squared errors using the logistic function to find the distance between the error, the data and the model. But in practice, what we can do is just write out the function and put that into a curve fitting algorithm, which is pre-built to be able to do these things for us. So we generally don't have to define the objective function. Okay, so I'm just going to run a little example here. This might be better to go back to the notebook. So all I'm doing here, I've just imported SciPy optimized curve fit as curve fit. I'm giving it the logistic f, which you'll remember I defined at the very beginning, which is just the logistic. And then I'm giving it our x values, which are the horizontal values. In this case, that's time. And then I'm using the y values, Twitter active users, in this next entry. And then here, these are our parameter values. So this is p0, our parameter guess. I've already, we walked through setting up alpha 0, gamma 0, and lambda 0 using just an initial guess to get us in the ballpark. I'm just using those same guesses here. So if I run this, I get two things. The first one we'll talk about are the standard errors. So we have the covariance. So this is just the output of the model. This uses that whole apparatus of the Jacobian we talked about here. This is just giving us this thing. It computes the Jacobian, computes the standard deviation of the sample, or the variance of the sample, and then computes the variance for the model. So this is looking at the variability. We have the variability in the data, right? You remember this distinction? We have the variability of the data itself, which is the standard deviation, or the variance. That's our sigma hat. I can just compute directly from the sample the variability. But then I need something else to tell me the standard error, like how wide this is. These are not the same measures of variability, even though we use one to compute the other. This one is computed using, you may remember this from your statistics class. This is like sigma over the square root of n. That's essentially what this is doing. This gives us the shape of the distribution. So here we have the covariance. So we have variability on the diagonal, and then covariances on the sides. And if you think about why this is a 3x3 matrix, this is when you're thinking about the size of these matrices and how you're multiplying them together, this just turns into a k by k matrix. Just with k being the size, the number of parameters we're working with. Okay, so nice. So that's awfully nice. So code just does all that backend work for us. I think the most important thing to know here, and I think the thing that trips people up the most, is this distinction between the variability in the sample, which is our sigma hat, and the standard error, or the variability in the model parameters, which is this thing. So when we talk about the variability in the model, it's about how confident we are that our model parameters are close to the truth. It's like the distribution of betas themselves. Every time we were to run the sample, like collect a new sample, the slope itself will be slightly different, and we want some way of understanding the distribution of those slopes. Okay, any questions here? Maybe I'm projecting, but that's the part I think I missed when I was younger, this distinction. And it's, so we have the variability in the parameters, which comes from how confident we are from the central limit theorem, and then we have the variability in the actual data points themselves. Okay, so that's the covariance. We can get the standard errors just by taking the square root of the diagonals of the covariance. So we don't actually care so much about the off diagonals. These are sort of the covariance between the model parameters. So in our regression context, that's the relation. So every time we were to fit a new model, we move both the beta 0 and we move the beta 1. So we, because we're picking both of those things, they can be related to each other. That's the off diagonal of the covariance matrix. But here we're just going to care about the diagonals. So this is the standard error for the first beta, which turns out to be alpha. So if we run this, we're just taking the square root, which gives us the standard errors. So I have the prediction itself, and then the standard error. This is equivalent to the standard deviation of the sampling distribution of the parameter. That's what the sampling the standard error tells us. So nice. So this is everything we need. Then we can use all of this to do all of the standard inference things. So we can construct 95% confidence intervals if we wish. And that's what I've done here. Y'all are, I think, probably super competent in these things. Correct? Like high competence. I'll take that as a yes. Yeah, that's what I like to hear. And if you don't feel totally competent in this stuff, you have all the resources to become competent. So I'm going to not dawdle on how we do this. Here we're just using the critical value, so how many t statistics on either side, and then multiply that by the standard error. So it's like how many standard errors away from the sample are we going to construct the confidence interval? Well, we multiply the critical value, the number of t statistics on either side, times the standard error to give us the confidence interval. Okay, so it gives us upper and lower, which looks like this. So we've just gone through and constructed the confidence intervals from the data themselves. And all of this, just like before, relies on these notions of central limit theorem, right? We're increasing the sample size. The only difference is that it's a nonlinear relationship. So it becomes more complicated in the ways you'd expect. Any questions here? Okay, so this is our variance covariance matrix. I don't remember why I have this in there twice. Okay, so the next thing we'll talk about, if you don't have questions about that, we can use our model results to make predictions out of sample. So if our data generating process is truly a logistic function, and we've gone in and estimated the logistic function on the data that we see, we can also extrapolate beyond the domain of the model. Whenever you do this, you should proceed with caution, not just in nonlinear models, but also in linear models. Whatever your function is, if you're making claims out of sample domain, then you should be very cautious about making claims there. What I'm going to do is attempt it, but you should view this with caution. So what I'm going to do, I'm just going to make some predictions. So I have a data frame here, which are times that go before 0. So it's 0 and then many times before 0. You'll remember the original data. Let's see. What was our data called? Twitter US. So you'll remember the first data points started at time 1. So what if we were to go earlier than time 1? We can use, if our logistic function is credible and we have enough data to estimate the model well enough, then we can make claims that go earlier than our data starts. So these are just some predictions, and then I'm going to plot these predictions in a figure. So this is the whole data set in blue, but I've now just constructed some predictions. And these go before time 0. So this is time 0, and I'm making predictions before the domain of the data. So it's outside of sample. And you can see there's no variability here. This is just, we take the x dimension, our time, and plug that into the model to get the model predictions. So we can do this. You should be very careful about this, though, as I'm going to show you a picture of why we should be careful. Y'all like pictures? The correct answer is no. We just want you to talk without any visual aid. Everyone loves that. Okay, so what I'm going to do is build 2 models and compare them. One, so I know something about logistic growth, right? I know that's generally how growth curves look. It must be. There's like a constraint on the world that forces the data to kind of look this way. But what if I didn't know that? Like, a lot of times we're going to enter contexts where we don't actually have a good idea about what the underlying data generating process actually looks like. So I'm going to compare 2 models. I'm going to use nonlinear least squares with a logistic function, and I'm going to use a polynomial regression, which is just a linear. The way I'm going to do it is just I'll have 2 terms, one for time and then one for like time squared, to give us some curvature to the model. I might even have a cubic in there. Yeah, I have a cubic, so we have time cubed as well. So I'm going to do 2 things. I have so the x and the y data, and then I'm going to use a polynomial fit on this. So this is just a regression, but of cubic polynomial. And then I'm going to run this. I'm going to and then plot both models side by side to give us a picture of what they look like. So this is, I have in yellow the nonlinear least squares using a logistic, and then I have a cubic polynomial. So this is, I have the data and I've fit, if you're not familiar with what this looks like, it's like, we have y is equal to beta 0 plus beta 1 times t plus beta 2 times t squared plus beta 3 times t cubed. What's the error? So I'm estimating this one. This is squarely within OLS, or general linear model. And I've fit both of these on the data. This first picture, this is within sample. And you can see, if you're just looking within sample, I mean, like, both of them look pretty good. The problem is, if we were to make extrapolations beyond the sample domain, they give us very, very different answers, right? If we were to make predictions using negative time, or at negative time, using our polynomial, it would give us negative users, which first off is just like, we know this to be wrong. But sometimes like the numbers will not be so clearly wrong. So you can see the models give us very different predictions about out of sample. So this is a word of caution. When this is a valid, I mean, this is linear, but we could perform the same steps we did for the nonlinear optimizer on this function, and we would get a model that looks like the one we have in blue. So the word of caution is that the model function that you pick determines the predictions out of sample. So just be careful with the kind of claims you make outside of sample. Like, I know that Twitter must follow some logistic growth function. generally. Like if Twitter, I mean, Twitter's, like companies will collapse eventually. So eventually this will come down. But for a good portion of the data, it sort of must be logistic. But if you didn't know that, you should be very careful about out of sample. Okay, any questions here? Yeah, Wei.
Generally, why would we want to use like out of sample?
Yeah, so good question. So the question is, why would we want to make out of sample claims? Well, let's say, so if you collect data on like housing values, for example, and you're thinking about, well, what would be the value of a, I don't know, like a house in a particular neighborhood where there aren't comparisons, you would want to know, like, you would use a statistical model to predict the property values of that house. But if there's no like good reference, you would predict the value of the house outside of sample. So like in my neighborhood, there are no mansions. What would be the value of a mansion in my neighborhood? That would be an out of sample prediction. So those kinds of things we do value in some cases. Yeah, so that's maybe an example. Or with your capstone project, like I know you're running into like selection problems. And what you want to do is make claims about what would happen to, I actually don't know all the details of your problem, but like how do you make claims about the, like if there weren't selection going on. And that's sort of like an outside of sample kind of claim. So we really do like to do these things. It's just you have to be very careful with how you implement them. Yeah, good question. What else? Okay, so nice. This is a big part of what we do. I'm going to show you another way that we can break nonlinear regression. So I have Snapchat data, and I want to show you what it looks like. So this is over a similar time horizon. We have this going from 2014 up to just about pre-COVID, or right in COVID. And you can see like there's this weird little thing here. I wonder if this is like a data error, like a way they're keeping track of how many users they have, because it jumps up. So it might be like a reporting metric that they implement here, and then they pull it back. I'm not sure why it looks like that. But let's say, I mean, it looks linear, but Snapchat data, like in theory, should follow a logistic growth curve, right? Like there's a cap on how many users there can be. And like the reason it grows exponentially is it's a social network. Like the number of users is proportional to its growth until it starts maxing out. So let's try to estimate this function, the logistic, on the Snapchat data. And you may already be starting to see some red flags, right? Like, how are we going to get any idea about curvature? So we need some curvature to tell us about the rate of growth. We need some curvature to tell us where it starts and where it's going to end up. We don't need to see the whole shape, but we need some curvature, at least in the middle, to give us some claims about even the curvature in the middle. Like if we just have enough curvature here, and we know that it's a logistic, we can then extrapolate beyond beyond those intermediate values. But we don't see any curvature, really. At least I don't. But let's say we see this, we know these problems, and we just push ahead. What happens in this case? Well, I'm going to make an alpha claim. I'm going to say, look, if I'm giving it initial values, I'm going to say I have you know, the maximum at 250, but I'm going to say, let's just guess that it hits 300. So let's guess alpha to be 300, and then I'm just going to plug in some extra values here. This is the F0. So for gamma, we'll use the smallest value, and then I'm just going to plug this in. So this 15 comes from right around maybe the middle, like the fastest growing portion. Okay, so I'm just going to plot these out. These are the values themselves. And then I'm going to actually go through and fit this. So just like we did before, I have the covariance, I have the actual estimates, and then I'm going to curve fit. This is the logistic. I'm giving the t values as the x, and I'm giving the snapshot daily users as the values, and then these are my parameter guesses. I run this, and I get these estimated parameters. So I guessed, what did I guess? 300, and alpha turns out to be 235. So we're saying it maxes out right around here. First red flag. Everyone see that? Then I get a gamma, so this is the minimum. This is hard to tell, so maybe not a red flag. And then I see the lambda. Hard to interpret the lambda, so I see no red flags yet. The standard errors look fine though. So these are within reasonable size. So standard errors look fine. Does this mean the model is well identified? I mean, first thing I see when I'm looking at this is that alpha looks totally wrong. One question you might have is, you know, how sensitive is this to different values of alpha? So what I'm going to do here, I'm just going to plot the model itself and then plot that with the data. So this is the fitted model, and this is the data. And you can see, like, part of what's going on here, we have this nice, we're like putting the flat portion of the logistic on top of most of the flat portion of the data. But this thing does not look like it matches at all. We sort of, we don't quite have enough curvature to be able to pick out where the curve starts, or like kind of how the shape plays out. Okay, so this is part of what we call the identification problem, or like weak identification problem. The curve is flat. If we zoom out to larger values for alpha, it would barely affect the fit, right? Like if I were to raise the alpha up, it would, like, you can just see it visually. Like, we're just going to stretch this thing out, and it's not going to change the fit that much. So what's going on behind the scenes is the optimizer doesn't, like, there's not much slope to the objective function. So it doesn't quite know where to move. So picking the alpha value is pretty challenging here. This is what we call the weak identification problem. There's not really enough data to get the curvature right. You all have talked about identification a little bit, maybe, in your econometrics. Okay. I'll take that as we saw it. And identification is just, can you build the model from your data? and is your model correct with your data? So that's the core problem here, is we just don't have enough curvature. Another thing we can do is, you want to make this worse. In addition to so we could like change the function. So in addition to this thing, we can also add like an intercept. So I'm going to add an intercept term, just call this C. So this is just the same function as before, just shifted up or down by C. And then all I'm going to do is run this on Twitter. So this is, we've introduced one more parameter, which gives, so we have now 4 parameters instead of 3. And our estimate for alpha, if you remember back, it was right just over 68. That hasn't changed much. Gamma, I think, also hasn't changed much. Lambda, I think this also hasn't changed much, which is nice. So what I'm going to do here is just plot the new model with our intercept. You can see the intercept is positive, which is nice. So again, this looks really, really nice. Lots of the same, like a really nice fit. But when we moved to snapshots, we were looking at the Twitter data. Again, this second approach, or the approach with Snapchat data, it's going to fail in extraordinary and similar ways. So here, we're just going to take the objective function and then minimize it. And I'm going to do this a couple of times. I'm going to show you, so we're using Nelder-Mead, but I'm going to show you what happens as we run this a couple of times. So the first round, and the reason we're using minimize and not the curve fit we just used is here we can actually get a sense of whether it's converged or not. Curve fit may be able to do this, but this is just a cleaner visualization of it. So I'm minimizing the objective function with the intercept on the Snapchat data. First round, did it converge? No. So I have these parameter values for each of the 4. So alpha, gamma, lambda, and C. And then I'm also getting the sum of squared residuals. So this is how wrong the model is. I'm going to run this a second time. Instead of using my original guesses, I'm going to plug in the parameter values that I got from the first round. So sort of just like we did with Newton-Raphson, I'm going to take the guess, plug that into the function, return an optimized value. And then I'm going to take that optimized value and put it back in again. It said it didn't converge, so maybe we just need to keep running it. And that's what I'm going to do. So here, I've just put it in a second time. The second time, it's also not converged. And let's take a look at the parameter values. This one is very different. So alpha turned out to be very different in the second round. It's not even close. This is, scientific notation for 2 extra zeros, 2 more decimal places. So this is like 630, which is way outside of what we had. So it's saying we're now at 630 on the vertical axis, which doesn't seem right to me at all. But how can we tell? Then for the second round, it's continued to increase. So now with scientific notation, we're moving 3 decimal places. So this is, what's that? 1, 2, 3. So that's 1,198. So we're continuing to increase the alpha. If I run this again, I'm going to get different numbers again. Third round has also not converged. I'm still in 3, alpha is right around 1,600. You can also look at the other parameters and see they're changing a little bit. So it's not just the alpha parameter, but all of them are changing. C is getting smaller. So we're simultaneously increasing the upper limit and decreasing the lower limit. The vertical intercept is now negative. So we're like spreading this thing out. And you may get an intuitive sense for why this is happening. There's no curvature, so we can't tell where those bounds are. So all we're doing is just like, we can get better and better fits by making that local approximation to the data as flat as possible. And the way we do that is by spreading the logistic function out. So that's what's happening here. And this is just totally unreasonable. Okay, so nice. We don't get any convergence. If we compare all three of these together, we might be able to see something interesting happening. So we just talked through some of the alpha parameters and the intercepts. But you can also look at the sum of squared errors, sum squared residuals. They're all about the same. They're slightly different, but they're pretty close to each other. This is telling us that as we continue to move on the gradient, it's we can continue to descend slightly, but there's not like the steepness of the landscape is not very severe. And what this is telling us is like we don't have, like this is part of the weak identification problem. Like we don't have enough curvature to give us a good idea about where our local minimum is. And you can see that in this sum of squared residuals. So we don't get convergence. Okay. And then if we're trying to make out of sample predictions, these are the models. So round 1 is in yellow, and then round 3 is in red. And you can see it's starting, like the peak is getting higher, and then the vertical intercept is getting smaller, in fact going to negative values. Okay, and then let's make some predictions at time 80. And here you can see the predictions are just very, very different. All right, any questions here? What's the takeaway? It's really only as good as the model that goes into it. I want you to be thinking about OLS as one example of nonlinear least squares, that we just happen to be able to take a first derivative to optimize. But the linear models you're familiar with are just one functional form of the kinds of things we've been doing. It's just here we can take the derivative and maximize enclosed and minimize enclosed form. The general solution depends on the functional form you give it, including the linear one. So be careful when you're setting up your data. Really, the model you use, or the output of your model is only as good as the model you choose, and then how you solve it. Okay. And in some ways, like using nonlinear models kind of makes your results a little more fragile because you have more things to pick from. If you're forced to use only linear models, in some ways that's a constraint that can be helpful. But I'm not sure I'd go that far. Okay. Can I show you one last example and then we'll take off? And then we'll do quantile regression next time. I'll take that as a yes. I was looking at my computer, so I didn't actually check. So we don't need nonlinear least squares for everything. Some kinds of problems can be solved with linear regression, even if they're nonlinear. I mentioned Cobb-Douglas, so this is one of those classic examples of linearization. And I think you've worked with this in your either, I know a lot of you took intermediate here. We do this in intermediate, at least we usually do. When we're solving the optimization of a Cobb-Douglas, one of the the tricks for solving these is to linearize it. So we take a log of both sides, and because we have a product on the, the right-hand side? Don't ask me for directions or for spelling. I haven't found a spelling error in my notebook yet. If you take a log of both sides, you get log y, and then we get, from the properties of logarithms, we get the log of the base times the exponent. So here we have, and then it's just additive. So it's, looks like this. I think you all are familiar with how this works. But part of the reason we developed Cobb-Douglas, like, you know the famous story of how this thing was developed. Like, it was either Cobb or Douglas was a economist at Chicago who called Cobb or Douglas the other one, who was a mathematician. I think he was at University of St. Louis, and it was like, hey, can you make a nice production function that behaves well mathematically? It also turns out that all of the nice properties for solving Cobb-Douglas, where there's like an interior solution guaranteed, either in the utility maximization problem or the like isoquant version, all of those same properties are nice when we think about like actually going in estimating the parameter values. Here you can see this is exactly an OLS. We've taken a very nonlinear function, linearized it, and all we have to do is estimate for, this is our beta 0, the log of beta. Gamma is our beta 1. 1 minus gamma is our beta 2. And then we can just fit this equation. So if you're interested in where those exponents come from, like in your intermediate class, and I guess in the theory portion with Kevin, you probably did some of this, right? Like, where do those betas and alphas come from? We go to the data and we fit them. And we can do it using OLS by taking a log of the variables. So in this case, even though it's nonlinear, we can linearize it. There's a little bit more here to do with the way the error terms are constructed. So if the model looks like this, we can then take the log. But if we have a different error term, so when you take the log of this, you get the log of the error term, which is nice. But if it looks like this, then it's harder to take the log, right? Like, you'd need the log of two things added together is more complicated to handle. So just think about the assumptions that go into the models we're constructing. As I've showed you, the assumptions we make about the functional form impact the validity of our estimates, the weak identification problem. So why don't we leave it here? All right. These are always long classes. Like, I don't get tired by the end, but I think I would if I was sitting in the class. So I appreciate your careful attention. It's nice when folks are like here and being actively involved in the class. That makes my job a lot easier. So I appreciate that. I'll see you all tomorrow potentially. If you, here's my thing with extensions. I don't have any particular reason why you have to submit it on Friday. I impose that as a deadline to get you to do work. I like deadlines as a student. But if you can't be there on Friday, you have to do a little bit of work to get the extension. You have to ask me for it by email, but I'll give it to you. And when you send me your email, I'll also send you the PDF of the checkpoint. But I want, like, ideally, I think it's more fun and more rewarding, both personally for you, hopefully, and yeah, talking to me is always going to be personally rewarding for you. That's my claim. It may not be. But at least I think it will be more educational to sit down and be able to talk about questions that arise. So that's the point of what we're doing. It'll be ready by, so I have office hours for a different class at the beginning of the morning. It'll be ready maybe around noon and ready to go. Our office hours for the class are 1 to 3, so that will be the main portion of the checkpoint. But send me an email. I can give you an extension through like midweek.
So should we get there at noon or
Try to maybe come at 1.
1? Okay.
Yeah. But if you need to come earlier, that's also, like if you can't do those hours, we can also work around that. Nice seeing everyone. I think the weather is like tip-top today, so don't be inside.
You know, you said we would like vote or talk about it next Thursday, but this is like kind of the vibe for the checkpoints is going to these like office hours.
Yeah.
Okay.
It's a bit of an experiment. We can always adjust as we need to.
Okay.
But that's kind of the vibe, yeah.
I'm gonna send you an email because I usually work at 2 on Fridays, so I can't
Oh, okay.
come tomorrow, but I can move my schedule easily for like the next one.
We can also don't
It's
like
ju-
I think
just,
it's easier.
serving, so like I'll make more money working 5 to close anyway, so I
Okay.
can switch it around anyway Friday nights. So.
I'm also flexible on my end if you can't actually move it. So
Okay.
yeah.
I'll let you know,
Okay.
but I'd rather be there in person to like talk with everyone else.
Yeah.
Terminate the process.
Okay.
Using Control C and then put the criminal.
I think also continuing tomorrow specifically is just because there's like a funeral.